Good morning, everyone, and welcome to Physics 302, the spring 2022. Today, we'll be reviewing the contents of Module 8, the final module in this course. But before then, let's take a look at what is due this week. In the announcement section in Blackboard, you would see that this week, quiz number 8 was due yesterday, together with reading assignment number 21. And the post-test for module 8 is due by the end of today. And of course, you're working on your class presentations. The submission link is live since Sunday, and you should be able to submit your presentations and reflections once you've completed your work. But you have up to the 21st of April to complete the class presentation activity. And after today, we don't have any meeting until after the Easter break, because we have this Easter break runs from Thursday, April 14 to the following Monday. And still on Blackboard, in the announcement sections, you will see I posted a video because some of you had complained you had difficulty recording on Mac computers. And I posted this video that walks you through the process of recording your screen directly to Flipgrid. So you can literally go into the Flipgrid topic for presentations and click add a response, and then choose screen recording or capture screen. And so the understanding is that you would already have your PowerPoint prepared, and then you launch it on your screen, and then go to Flipgrid and just record it directly as you present. Flipgrid will capture your voice and the slides displayed on your screen all at once. So if the separate recording in PowerPoint doesn't work for you, you can use this method, and this works both for Mac and Windows computers. But I will not be accepting any emailed presentations, because I wanted to come away from this activity with a new skill. This what you're doing now is not just for the 10% for the grade, but you're learning a new skill that may be very useful for you in your career, your future job, and so on. You would need to be able to create explanatory tutorials and things like that. So this is a skill that I want you to come away with from this course besides the physics. So don't take a shortcut. Don't try to take your cell phone and record your screen while you're presenting. That will not be accepted. So you have to use one of these methods. Either use your PowerPoint recording inside PowerPoint, or use any video application on your computer, or directly use Flipgrid to record your screen while presenting. Are there any questions concerning the announcements and everything up to this point?
No.
No questions. Okay, so I take it that everyone is on track, or everyone knows what they're doing, and I really expect everyone to submit a presentation that will meet, or that will enable you get, full credit, the 100%, because this is not really a test or an exam. is more about you being able to search information and present it in a logical manner within the guidelines provided. And if any of the guidelines is not clear, you have enough time to reach out and have any doubt cleared, before you submit your work. So take full advantage of this. But at the same time, it's not like if you submit anything, you're going to get 100%. So your work still has to be of the highest quality. But I'm here to provide the guidance and the support to make sure, every student's work will meet the highest standards, for the maximum possible grade. So if there are no further questions, before we move into the overview of Module 8, I'll just remind all the graduating seniors that I'm going to send out a separate email just to the seniors, directing them once their exam window has been set up. So you can go ahead and set up your appointment before the Easter break. Don't wait until after the break, because you may already be within the 72-hour cutoff. But once you get the email, log into your Proctory account and set up your Proctory appointment for the final exam. And when we come back from Easter break, we will have a review session dedicated for the graduating seniors. But tomorrow's session, we're going to have a tutorial session tomorrow in the evening. So I encourage all graduating seniors to sign up. If you have any questions, remember it's a comprehensive final exam. So if you have any questions from modules 1 up to where we are, I'll be glad to discuss that with you tomorrow during the tutorial session. Obviously, Easter break starts on Thursday, so there will be no evening tutorial on Thursday, but we'll have a tutorial session on Wednesday evening. And then the Tuesday following the Easter break, we will have a review session during the class, and the priority will be questions from graduating seniors. Okay, so Module 8, the topic of Module 8 is electromagnetic induction. And the main idea behind the concept of electromagnetic induction is the fact that electricity and magnetism are intricately related. So electric fields give rise to magnetic fields, and changing magnetic fields give rise to electric fields. So a crucial concept in introducing the topic of electromagnetic induction is the concept of magnetic flux. So magnetic flux is denoted by the Greek symbol phi. Some of you who are members of sororities, you guys use all the symbols, kappa, gamma, epsilon, phi, lambda, and so on. So it's a common practice to represent physics quantities using these symbols. So the magnetic flux phi is is related to basically to the strength of the magnetic field, or the magnetic field, the number of magnetic field lines crossing a surface area. And it is defined in equation form. The magnetic flux is equal to the magnetic field density, B, multiplied by the area, multiplied by the cosine of the angle between the area, or the direction perpendicular to the area, and the magnetic field. So here, B is magnetic field strength or density. That's like the number of lines per unit area. A is the area, and then theta is the angle between the magnetic field and the direction perpendicular to the area. Or you could also say it's the direction between B and the normal vector. Normal vector is simply a vector that is perpendicular to the area and points outwards or away from the area. And this is where many students often get confused, because it's tempting to say, since this equation is B times A times cosine of theta, it's tempting to just assume that theta is the angle between B and A. That is not true. It is the angle between B and the direction perpendicular to A. And that's entirely different, because if you're given a diagram and then you use the angle between B and A, you arrive at the wrong answer. And so the SI units is the Tesla. Sorry, the SI unit is Tesla times meter squared, or the Weber. So Tesla times meters squared, because Tesla is the unit of magnetic field. Meter squared is the unit of area. Of course, theta doesn't have any units. It's just an angle. This is also measured in the Weber. So let's illustrate this. So suppose we have an area like this. So this conductor, this rectangular conductor, is lying on the plane of the screen. Now, suppose we have a magnetic field that is going across from left to right. Obviously, this is the magnetic field. The area of this is just the length of this multiplied by the width. If you look at this diagram, clearly you would see that the angle between the magnetic field and the normal vector, in this case, is 90 degrees, because the normal vector is a vector coming out of the screen towards you. So a vector coming out of the screen towards you, and then another vector going across the screen, the angle between the two is 90 degrees. And so the magnetic flux in this case is equal to B times A times cosine of 90 degrees. And cosine of 90 degrees, so you can all verify, is 0. So there is no flux in this case. And you can explain this by the fact that in this case, you know, this magnetic field lines, if you consider this as if you treat the magnetic field lines as arrows, you notice that the arrows, none of the arrows penetrates the plane of the conductor, because they're just going across. You have the conductor. You have the conductor line flat on the screen, and the arrows just going across it. None of it goes into the plane of the conductor. That's why the flux is 0. So no line is going through the conductor. And the same would be true if we had, I'm just going to draw multiple cases. So if we had something like this, this is your B. Again, here theta is 90 degrees because the normal is always coming out of the plane. So the field is going up, the normal is coming out. The direction between out and something lying on the screen is 90 degrees. So the flux again is 0. If we had a situation like this, and the magnetic field was going this way, as long as the magnetic field is on the plane of the screen, it's going to make an angle of 90 degrees with the outward direction, with the normal direction. So theta here is also 90 degrees, and the flux is 0. Now, if we had a situation like this, I'm trying to see if I can draw a 2. Well, I'll just use the convention we used earlier on. So let's say this is your conductor, and then I'm going to use this notation, which you should be familiar with. Previously, what did we say the dot represents when we studied magnetic fields? Does anybody remember this convention? This is the magnetic field. Can somebody tell me the direction of this magnetic field?
Is it in?
Close. Remember, we use this notation and this. What does the X represent? Think of it in terms of a screw. If you were saying the end of the screw that has an X on it, where you apply the driver, would the screw be going in or out?
You're saying if you were to tighten it?
If you're tightening a screw and you're seeing the side that has an X on it, will it be going in or out?
In.
If you're seeing the tip of the screw, will it be going in or coming out?
Out.
Out. So that's the notation we've used before. And I'm surprised that, more people in this class are not remembering this, because this is very crucial. If you forget this convention, then you may not be able to correctly understand some problems, let alone solve them, because you would encounter this notation throughout module 7 and 8. So in this example, these magnetic field lines are coming out of the page. So because they're coming out of the page, and we know that the normal vector by definition is also coming out of the page, then what is the angle between the normal line and the magnetic field? What is the angle between the normal line and the magnetic field? Jayla? Can you attempt? Kathleen Phillips, can you attempt this problem?
I'm not really sure.
Okay, so let's put it this way. You have two vectors pointing in the same direction. What is the angle between them?
There's no angle.
The angle is 0. If two vectors point in the same direction, the angle is 0. If two vectors point in opposite direction, the angle would be
180.
180 degrees. So this is 0, and the flux here is B times A times the cosine of 0 degrees. What is a cosine of 0 degrees?
1.
1. So the flux here is just B times A, and this is when the flux is maximum, when the magnetic field is perpendicular to the area. In other words, perpendicular just means it's in the same direction as the normal vector. So and you can see here, if we counted the lines, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines, all going through the plane of the conductor. And that's why the flux here is the maximum, because all the lines are going through. In the other cases, the lines were just flying across. None of the lines were actually going into or out of the plane of the conductor. Another example, if we had this time, let's say the flux is going so the flux is going into the plane of the conductor. So this is your flux, and it's going in. In this case, B is out. So what would the angle be in this case? Yvonne?
Can you repeat yourself?
What will the angle be in this situation where the flux, the field is going into the plane of the page?
I'm not quite sure.
Do you know the direction of the definition of the angle? The angle is between what and what? I can go back to the where we define the angle. Can you read this for us?
It says the angle where it says between B and the direction perpendicular to the area. Is that what you're saying?
Okay, that's the normal vector. And I told us that by definition, this direction is always out of the area or away from the area. So let's go back to this problem. So B is going into the page. It's going in, that's away from you, into the screen. What is the angle between B and the direction that is coming out of the page? That's the normal direction.
I don't know.
What's the angle between the direction away from you and towards you? If I drill on a two-dimensional surface, so let's say this is away and this is the other one towards you. What is the angle between these two directions that are opposite? One is going in, one is coming out. So the opposite each other. What is the angle?
It'd be 0.
No. 0 is when they're going the same direction. When things are opposite, what is the angle? What is this angle? Is that 0?
It's 180.
That's 180. That's half a circle, right? So here, B is going in, and then the normal vector is always coming out. So the direction between these two is 180 degrees. So basically, whenever the two vectors are opposite each other, the direction is, the angle is 180. When two vectors are in the same direction, it's 0. So the flux here is equal to B times A times cosine of 180. And this is just minus B times A because cosine of 180 is minus 1. Okay, so the flux here is negative, whereas in the other case it's positive. But if you take the absolute value, then the amount of flux here would be the same as the case where the angle is 0. So you have maximum flux when the angle between the flux and the normal vector is either 0 or 180. And then when the angle is in between 0 or 90, then you would use the full equation. You plug in the angle into the equation, B times A times the cosine of the angle, and then you get something between 0 and the maximum value of B times A. Any questions?
No.
Okay. So that is a flux, and you have to really understand this because if you cannot calculate flux, then you really cannot apply Faraday's law or Lenz's law, but those two hinge on the understanding of how magnetic flux is calculated. Now, so an example here would be a magnetic field of let's just say 1.0 times 10 to the minus 3 Tesla is directed into a rectangular conducting loop with dimensions. Uh, 10. Calculate the flux. Can somebody tell us where to start in this case?
Draw the magnetic field.
Okay, it may be good to do that. So how would it tell me what to draw?
You would draw a circle with an X in it.
Okay, where should I draw it?
Inside of the square or magnetic field.
Okay, so I need to start with a rectangle, right? It says rectangular, and the sides of the rectangle are what? 10 centimeters by 20. So the long side is 20 cm, the short side is 10 cm. And it says the magnetic field is directed into the plane of the page. I can just draw one or just a few circles with axes. That means the field is going in. Okay, so in this case, the angle is what? What is the angle in this case? We just did an example. When the field is in, what is the angle?
Is 0.
No. Right here, when the field is in, what is the angle?
180.
180, because the normal vector is always out of the area. So the direction, the angle between in and out direction is 180, because those two directions are opposite each other. So this is 180 degrees. What is the area? How do we get the area?
B times, I forgot the equation.
Shikari, how do we get the area of this conductor? Your response during class constitutes your attendance for today. So if I call on you more than once and you don't respond, then you will be considered absent even though you logged in.
Would
Even
it
if
be
you don't
20
know
centimeters
the
times
answer,
10
you can attempt,
centimeters?
or you just give your opinion. If you don't know at all where to start, you can also indicate that I need some kind of feedback from everyone that is active in the class.
Would it be 20 centimeters times 10 centimeters?
Okay, and which equation are you using?
You asked me how would I find the area. I was just asking if that was.
Yes, and I agree. Your answer is correct. 20 times 10, but I'm asking you, which formula are you using? Or why did you decide to do 20 times 10?
I decided to do 20 times 10 because that's how long the rectangle is. I didn't exactly use a formula. I was just going based off your drawing.
Okay, so basically, number one, the problem says it's rectangular. So for a rectangle, we know, or you've learned, that the area of a rectangle is length multiplied by width, right? That's what I just wanted to mention. So, because if this was not rectangular, you would probably do a different thing. If it was a circle, you would use a different equation because the area of a circle is pi times radius squared. If it was triangular, then you would be using the equation for a triangle. So be aware that it's not always length times width. It's length and width in this case because we have a rectangle. So this is 10. Sorry, the length is 20. And I'm going to, I always have the habit of converting to the SI unit. Centi, the word centi means 10 to the minus 2 or 100. So 20 centimeters becomes 20 times 10 to the minus 2 meters multiplied by 10 centimeters, which is also 10 times 10 to the minus 2. Okay. So basically 0.2 multiplied by 0.1, and that will give you 0.02 meters squared. Did anyone get the same answer? And I'm going to actually add 0 because I want to keep the same number of significant figures. My measurements, the length has 3 significant digits. The width has 3 significant digits, so the answer should have 3 significant digits. The 0 before the 2 is not significant. If we remember the rules for significant digits. So 0.0200 meters squared would be the correct number to the correct number of decimal, or to the correct number of significant digits. So now that we have this, we can proceed to plugging this into the actual equation. Phi equals B times A times the cosine of the angle. So B is 1 times 10 to the minus 3 Tesla. A is 0.0200 meters squared. And the angle is 180 degrees. So somebody work this out and tell us the answer. Everyone plug this into your calculators. Let's see if everyone gets the same answer. What is the answer? What do you get?
I got -2 times 10 to the -4.
Okay. So 0.02, if we want to write this in standard form, this will be 2 times 10 to the 1. Is it -1 or -2?
-2.
Okay. So if you do 1.0 times 10 to the -3, and then multiply by 2.00 times 10 to the -2, multiplied by -1, which is the cosine of 180, Okay, so 1 times 2 is 2, right? 10 to the negative 3 times 10 to the negative 2 is what? Is it negative 4 or negative 5? Can you verify your answer again? You must have done 0.2 rather than 0.02 to get 10 to the negative 4. I'm just showing you how you could work this problem without a calculator. I just did without using a calculator, just using my knowledge of standard scientific notation and the manipulation of indices, which you've learned, prior to this class. X to the A multiplied by X to the B is equal to X to the power A plus B. That's one of the rules. So if I'm multiplying 10, my 10 here is X, that's the base. So 10 to the minus 3 is A, and then minus 2 is B. 10 to the minus 3 multiplied by 10 to the minus 2 is 10 to the minus 3 plus minus 2. Minus 3 plus minus 2 is minus 5. Okay? So this is your magnetic flux. Any questions? Alisa, did you get the same answer?
Yes, I got the same answer.
Okay. Okay, so we're going to talk about let's talk about Faraday's law now. Again, this is a review. It's not a re-lecture because you have the recorded lecture. If you didn't review it, then that is on you. But to make the most of this class, you definitely need to, review the pre-recorded instructional videos before class, and then fill in the gaps when we meet like this. So Faraday's law deals with the changes in magnetic flux, and Faraday's law basically says that any change in magnetic flux induces an EMF, and in equation form, Faraday's law is written like this. The magnitude of the induced EMF is equal to the number of turns. So if you in the examples we did, you just have one loop of wire, but in most electrical devices, you have multiple loops. You have a wire that is wound round many times. So the number of times you wrap the wire is called turns. So if you wrap it 2 times, then it's 2 turns. We wrap it around 3 times, 3 turns. And the number of turns has an impact on the strength of the magnetic field or the EMF. So the number of turns multiplied by the change in magnetic flux divided by the time. Basically, any change in flux will cause an EMF. If the flux is constant, that means if there is no change in flux, then there will be no EMF. So if delta phi equals 0, there's no change in flux, then this 0 divided by delta t is 0, multiplied by n is 0. That means there's no induced EMF. So this is the equation form of Faraday's law. Any change in magnetic flux induces an EMF. And this is what is called electromagnetic induction. And this is the principle behind how electricity is generated. So basically, nature does not allow flux to change. So when the flux in any area is changed, either by varying the magnetic field or changing the area of the conductor, because flux depends on the magnetic field, the area, and the angle between the magnetic field and the perpendicular to the area. If any of those variables changes, causing the flux to change, then nature will react immediately to produce a counterflux that will restore the original flux. So if out of a sudden the flux in a given region increases by a certain amount, then nature will respond by creating an opposite flux to counter the increase. And if, on the other hand, the flux in a certain region decreased or dropped suddenly, nature will respond by creating new flux in the same sense to restore the reduced flux. So this process is what is called electromagnetic induction. And the flux that is created by nature, of course, will result in the generation of an EMF that can be used to drive current. And that's how, power companies generate electricity and then sell to you. So the electricity, in essence, is generated by nature, but of course, the power companies need equipment to harvest the electricity, to transport it over long distances, and then deliver it to your home. So what they're essentially selling is the cost of those services, but the electricity itself is generated by nature, by the process of electromagnetic induction. So let's take one concrete example. So for instance, the hydroelectricity is generated by water. So in a place where there's a waterfall, you can place a huge magnet with conductors around it, and as the water falls, you can cause those coils to rotate, and as the coils rotate, the angle between the magnetic field and the area of that conductor is constantly changing, causing the flux to change. And when this happens, then nature responds by creating counterflux to restore the original flux. And then the induced EMF is used to drive a current, which the power company now can collect and then step it up using transformers to a high voltage, and then transport it to where they're going to sell the power, and then step it down to save amounts of voltage and then deliver it to households. So that's a summary of how electricity is generated using the law of electromagnetic induction. Another example is the wind generated electricity. So the wind mill is rotated when the wind is blowing, and as the blades of the wind turbine rotate, obviously the area or the angle between the magnetic field and the direction perpendicular to the area is constantly changing, causing a change in flux. And then the induced flux, or EMF, is used to generate electricity that is transported or stored. You can store it in a battery or any energy storage device, and then use it to run devices that require electricity. So the key elements here, again, remember the flux is B times A times cosine of theta. So any change in B, in A, or theta will cause the change in flux. So in essence, to cause the flux to change or to create an induced EMF, all you need to do is change B, change A, or change the direction. So changing the direction, the easiest way is to just to make the area rotate. You make the conductor continuously rotate, then you're constantly changing the area, and that's how you can continuously cause an induced EMF, and that's related to how electric generators work. You have a coil that is constantly rotating, and as it's constantly rotating, the angle between the field, the normal to the area is constantly changing. Now, before we talk about Lenz's law, let's talk about motional EMF. So motional EMF is simply EMF induced by the motion of a conductor relative to a magnetic field. And the motional EMF is simply B times L times V, where B is the magnetic field, and L is the length of the conductor, V is the speed or the velocity of the conductor. And of course, so the length of the conductor is like the length that is moving perpendicular to the field. So for instance, if you have let's say you have a magnetic field everywhere into the page. And then you have the conductor moving into the field. This is your B. Your L is the length, this length. It's not this one. It's not this side. It's the length that is moving into the field. And I'm pointing that out because you maybe give her a conductor like this, and then they just say this is 5 cm, this is 8 cm. And then you'll be wondering whether you're going to use 5 or 8 as a length. So it's always the length, the side that is directed, that is perpendicular to the field or to the velocity. And we're going to run up with a discussion of Faraday's law. So, sorry, Lenz's law. we just discussed Faraday's law, so let's look at Lenz's law. So Lenz's law basically adds the minus sign to Faraday's law. So the negative n delta phi and the focus here is this negative sign. So the negative sign simply indicates the fact that the induced EMF always creates a flux to oppose the original change in flux. So induced EMF creates a flux that opposes the original change in flux. This sounds very trivial, but this is often widely misunderstood and misinterpreted by students. Remember, it says the induced EMF creates a flux that opposes, that's number one. And what does it oppose? It opposes the original change in flux. It doesn't oppose the original flux. And that's what students often, 90% of the time, will interpret this to mean. Like if the original flux was out, then Lenz's law says the new flux will be in. That's not correct. So you have two fluxes. You have the original one, which is there. And then when it changes, Faraday's law says there'll be an induced EMF, and the induced EMF will create its own flux, which is now the induced flux. So Lenz's law says the induced flux will always oppose the original change in flux. It will not always oppose the original flux. It will always oppose the original change. What do I mean by this? And if you watch the lecture, you should have, come across this discussion. So opposing a change is different from opposing something, because the change in this case refers to two things. So a flux can change by increasing or by decreasing. If neither of those two happens, then there's no change in flux, there's no induced EMF. So original flux so let's do something like a table here. So we have original flux, and then we have induced flux. So, so if the original flux is increasing, this is the change. So change in original flux is increasing. How do oppose something that is increasing? How do you oppose an increasing quantity?
You go against it.
You go against it. So because let's say something was at 10 and then it jumped to 15, but you don't want it to keep going up. You want to bring it back to 10. So you have to go against it. And in this case, if you're dealing with vectors, you just need to create vectors that are opposite so that the new vectors will cancel out the newly created vectors. So induced flux will be opposite to the original flux. Does that make sense to everyone?
Yes.
So the original flux is increasing. Lenz's law says the induced flux will oppose the original change, the change in the original flux. The change is increasing, you oppose an increasing quantity by decreasing it or by creating something opposite. Now, if the original flux was decreasing, how do you oppose something that is decreasing?
You go against it.
You're giving the same answer. So you cannot oppose an increasing quantity and a decreasing quantity by the same action, right? If a quantity is decreasing, let's use a real life example. Let's say the number of trees around you, let's say you're into preservation of the environment. You notice that the number of trees in your community is fast diminishing. How do you oppose that? How do you oppose the number of trees continuously disappearing? What action will you take to oppose this?
You add more.
You plant more trees, right? So you add more of that same quantity. So the induced flux now will be in the same direction. Again, flux here is just a magnetic field lines. Okay, so let's say you had 10 magnetic field lines that were going into the page, and out of a sudden the 10 lines drop to 8. So that's a decrease in flux. To restore it back to 10, you have to create 2 more lines also going in. That will bring it back to 10. So that's what Lenz's law says. If the original change is increasing, you will oppose it by creating something opposite. But if it's decreasing, then you enhance it. You create more of the same in the same direction, because the whole goal is to restore it to the original. And just for completeness sake, if the original flux is constant, what will happen according to Lenz's law? If the original flux is constant, it's not changing at all. Any attempt? I already gave the answer just before the last point. If the flux is constant, then there is no induced EMF or induced flux, because according to Faraday's law and Lenz's law, the induced EMF is N times the change in flux. So if the flux is constant, that means the change in flux is 0. 0 times N divided by delta T is 0. So there'll be no induced flux, no induced EMF. Nature will do nothing because nature wants the flux to be constant. So nature only kicks in when the flux decreases or when it increases. When it decreases, the reaction is to create new flux in the same sense. If it increases suddenly, then nature creates opposite flux to counteract the increase. And the whole goal is to return it to the constant value. So this is a summary of Lenz's law and Faraday's law that will be helpful together with the lecture, the recorded lecture. If you haven't reviewed it, then review it and use this table as a guide, to further understand how to apply Lenz's law. So for instance, let's take a simple example here. So I have a conducting loop, that is circular. Okay, and I'm going to get a magnet so we all know that, let me draw the magnet slightly further away. We know that a magnet, if this is the north and this is the south pole, or let's reverse it. This is south and this is north. We know that the magnetic field lines go away from the north towards the south pole. And all these lines extend into space. Okay, so this lines extend to infinity. So you can extend this all the way around, and there are infinitely many of these lines. I'm just illustrating a few. Now, if suddenly you pushed this magnet towards the conductor, what will happen to the number of lines that penetrate the plane of the conductor? Will it increase or will it decrease?
Can you repeat the question?
If you push the magnet in the direction shown by this arrow, so V shows the motion of the magnet, you push it towards the coil, the circular coil. What will happen to the number of magnetic field lines that go through the coil? Will it increase or decrease?
Decrease.
If you push this magnet into the coil, will you have more lines going into the coil, or will you have less lines going through the coil?
You'll have more going through.
You have more. Right now, you only have 4 lines, like going into the coil or touching the coil. But as you push the magnet closer into the coil, the other lines will begin to cross the plane of the coil. That's what I mean. So if the magnet is moving like this, then you would say the original flux is increasing. And if you go to the table that we just generated, Lenz's law says the induced EMF will oppose this change. You oppose increasing flux by doing what? By creating flux. Is it same direction or opposite direction?
You said, can you repeat the question again?
If the original flux is increasing, how do you oppose it?
You go against it.
You go against it. So induced flux will be opposite, right? So that means if the original flux is going to the right, from left to right, the induced flux will go opposite, will go against the original flux. It will go from right to left. So you have flux coming this way. Okay. It's difficult to visualize because this is, I'm trying to show a two-dimensional thing on a one-dimensional surface. But basically, if you look at the loop as my hand, so the original flux is coming from left to right, the other flux will be coming in the other way. And if you apply the right-hand rule for the magnetic fields and current, you will notice that for this to happen, then your current will have to go like in the counterclockwise direction. So if this is your conductor, for you to have a magnetic field coming this way, your current will need to be going like this. So basically you place your thumb in the direction of the current and then you wrap your fingers around and you see that the only way you achieve this is to have a counterclockwise current. So for this situation, just by plunging this magnet into this stationary coil, nature will create a current in this loop, which is counterclockwise, according to Lenz's law. And this is the current that you can then use for different purposes. If you have enough loops, you can generate a big enough current that you can either store in a battery or transport and use elsewhere. And this is what the power company does, essentially, to generate electricity. So we will stop here today and to give you time to transition to your other classes. But this is like our last overview, because this is the final module. But when we come back from the spring break, we will have the general review sessions to review content from all the 8 modules in preparation for the comprehensive final exam. Again, graduating seniors, watch out for the email about the ProctorU window so you can set up your appointments before going on spring break. And do not forget to take advantage of tomorrow's tutorial session. Sign up through Navigate, set up an appointment, and I'll see you during the tutorial session. So have a good rest of your day and a good Easter break if you don't, for those that